Do you hear me, Cliff? Cliff, are you there? But you can't hear me. Ah, good. Are you watching TV there too? I was going to say that sounded like it might be Maria Bartiromo in the background. Okay. I guess they all sound similar in some ways. Hello, Shreya. How are you? And Rami, how are you? Okay. If you take your mute off, maybe you can say hello. Zeke, how are you?
Good.
Good. Good. Okay. Pretty good. Four people already. I'm enthused by that. Four anonymous shadow faces, but that's okay. Privacy is one of your options in the remote setting. I guess we'll give another couple of minutes, even though it is 7 o'clock in the East. I happen to be in Austin, Texas today. I'm doing some work down here, so consequently, the remote session. And but while we're waiting, go to if you prefer, go to ISL Python site, resources, download Python, download. We're going to start by talking about uh, some of the slides in the Python book, the yellow book that we got for free from the good people at Stanford. That I think you looked at some with Professor McDonald, and that we also talked about in the context of principal components analysis. Hello, Yuming. We are on a roll here.
Hi.
I'm going to see what happens. I want to test out a sharing of my screen. I've got my iPad up here so that I could actually write on the slides as we talk. Let's see. Okay, let's see if I can share that. Okay, so we'll start here. This is the best I can do on sharing it. Um, so tree-based methods are a topic we have not discussed yet, or nor was it discussed in Professor McDonald's class. When we talk about both classification and regression problems, tree-based methods are one of the most effective methods for getting good accuracy and good explanatory power. And we're going to look at how decision trees are formed, which is the simplest case, not the most effective, but uh, the case that helps us to understand the method. And then we'll look at how decision trees are combined into random forests, which are many trees created somewhat randomly. Um, and So we'll learn how to build a decision tree, and then a random forest will build thousands potentially of small decision trees with a somewhat random component to how that the decision on the tree is whether to go left or right. We'll see what a tree this means in a second, and then when we ask a question, make a prediction on this particular next item, the decision tree will vote on each of the trees in the random forest will vote on what the answer is, and this ensemble method will generate results which have better, more accuracy and less variance, less bias than a single a single tree will have. Uh, as discussed here, we'll find that these tree-based methods are easy to understand, which is a positive for machine learning models. As you know, some of the complaints about various uses of machine learning in context like identifying criminals, for example, or potential bad folk, or screening resumes out of jobs, is that they tend to have a bias, which if the methods are a black box, you don't understand how decisions were made, and humans get a little disturbed when machines are deciding what's going on, but they don't have a way to explain it. But we'll see tree-based methods have a decent way to explain it, and then the methods that we use to make the tree-based methods better, they lose some of that or a lot of that simplicity, but they end up with good results. So we'll talk about the concepts of bagging, which I believe you may have talked about with Professor McDonald, bootstrap aggregation, random forest, which I just talked about, and boosting, which is, we'll see, almost the pièce de résistance, the best of all tree-based methods. And for data sets that are not as extensive as you might find in a visual application. So, for example, when Tesla and Waymo are training cars on how to drive through streets, they use many millions of data points in order to train the neural network models that are used to guide the vehicles in response to traffic. But many data sets are not so complete that these methods, neural networks models, can be fit. Consequently, simpler methods are needed, and this is where boosting gradient boosted machines, as they're known, becomes the second best method for many types of problems. The idea of combining a large number of trees can give dramatic improvements in prediction accuracy. You may have talked about with Professor McDonald. This is what's known as ensemble learning. So ensemble learning, as we said, basically means that you create many predictions, and then you let the predictions vote on what many predictors. And then when it comes time to make a new prediction, you let each one of the predictors have a vote, and you do some version of majority rules to decide what the correct prediction should be. So this example here, hopefully Jose joins soon, because it's a baseball example. Are you there, Jose? Okay. Uh, in this graph, in this table, we have one way to represent three-dimensional data in two-dimensional space is by using a normal XY plane and then representing different data points by colors. Um, in this case, low salaries are represented by blues and greens, and higher salaries are represented by reds and yellows. So the concept here is that we're going to use two features: how long someone has been playing and how many hits they have on average or in their last year. So you can think of this for any job, right? How much experience does the individual have, and how did they do on your preferred performance metric for last year on your X and Y axes, and then the dots reveal uh, what their salary was. So we see things like, you might notice that there are some people who have a lot of hits, and yet their salaries are red. But some of them, so the people with 5 years experience, it does appear that going up on average, you go from blue to green to light green to yellow to red. So certainly you do appear to make more money at the 5 year level if you have more hits. But on the 1 year level, the first, the new starter in a company or in a baseball team, regardless of how well they did last year. So this would be like their year two, I guess. 1 year of experience means they're second year players, right? They all pretty much are getting paid the same, except for these two make a little bit more. And then you go into year two, and you can see the salaries do start to creep up. You get more blue, and then you get more blue and green over here. And as you get over to year five, some of them get yellow. And then when you get to year five, 5 years of experience means they're 6 years in the league. They are the 6 years on the job, let's say. The blues and greens begin to give way to the yellows and the reds. And then when you finally get way over here, someone who's been playing a long time but doesn't have that much performance isn't paid that much, but who has excellent performance. Generally speaking, 200 hits is sort of a golden season in baseball, but 150 hits could be evidence of a very good season, especially if someone hits a lot of home runs, for example. Okay. So that's the data. And then the question is, given this type of data, we get information on a new employee who has X years of experience and has, a success ratio, a hit ratio, as it were, of Y. How much do we predict they will be paid? And in fact, you could see how this type of data would be used by human resource departments and baseball agents to argue for higher or lower salaries in the context of their advisor. And also, if you're someone looking at these data and you're charged with making a decision, you get to understand the market. You say, if I'm looking at someone who's in this high red quadrant, he has this lots of experience and also has been successful in his most recent year. We can anticipate that that player is probably going to command a high salary. And if we choose to enter into competition to hire that person, we need to be prepared to pay those rates. And if we're not prepared to pay those rates, this model would tell us that we are probably going to lose that player if that's our goal. So the way a decision tree works is, in this case, notice we only have two features. Features are the X's. Think of your linear regression model as being, y equals m plus a1 x1 plus a2 x2 plus a3 x3. The x's are your features, the inputs to the linear regression model. The a's are the coefficients, how important each feature is to determining the output, which is the y value, which is a single number in the case of a linear regression, or which is a classification in the case of logistic regression, for example, or other classification models. So what this tree does, it looks at it tries to we'll get a moment to see how it makes its decisions, but let's just look at what it decided here. In here it says, look, if they have less than 4.5 years, I'm going to send them to the left tree and end up at this number 5. We'll see in a moment what the 5 means. If they have more than 4, so this is a true or false, yes or no. So the player comes in with this much experience, we send them over here, and we predict he will be paid 5. If the player is a no, so they come over here, we actually choose now to make another decision. We look at the number of hits they have. And naturally, if they have more success If they have less success, their hit numbers are lower. We pay them 6. And if they have more success, we pay them a bigger number, 6.474. And if you read the notes associated with this, with these slides or in the book, we learn that these are the log of their salaries. So since 5 is the log, you take E on your calculator to the 5th power. And hold on a second. Let me clear my calculator. You take E, oops, I don't want that. I want E to the x5 power. Okay, clear. Okay. E to the 5th power is 148,000. Now, this book probably was first written in, I think the first edition in R was probably written at around 2000. So this data is, significantly out of date for modern salaries. But, E to the 5th power is still $150,000, which isn't a bad salary. It's just we know baseball players tend to make more. You take E to the 6th power and you get 403,000. So this number over here, 403, a lot bigger than 511. And if you take E to the 6.74 power, you get 845,000. So those numbers again are basically 150,000, 460, whatever that was, and 845,000. So it's a pretty big span. It looks small because 5, 6, and 6.7 are so close to each other. But once you take the exponential of those numbers, you get much bigger numbers. You have to understand that it's in thousands as well. You always need to understand your data, right? How is my data given to me? Why do they choose to take the logarithms before they make this split? They don't discuss that in the book, but there are some interesting reasons in statistics. Does anybody know why we might take the logarithm in statistics in order to before we analyze a set of data? There's a kind of a Yeah, no, this one's not about stationarity, but that's a good hypothesis. There's a slightly different reason. You might want to ask your local ask your LLM, your AI brain, why take the log when doing statistics? In what cases do we take the log? And the answer should come back something like, if you have data sets which are skewed to the right, taking the natural logarithm will make them look more like a normal distribution, i.e., more symmetric. And many modeling frameworks work better when the data is approximately normal. When data is not approximately normal, you may spend a lot of your error budget trying to fit the outliers. That's probably going to be the explanation you'll get. And you should definitely type that into your LLM if you haven't done so already. Well, you know what? Let's just go ahead and let's see if I can. Yeah, I think I'll lose the screen, but let's just see what happens here. I hit Gemini up. Okay, EMI. Okay. And this is clear. Look, we're only 2 years into this revolution, and all of my teaching has started, and all of my thinking has really started to evolve in this way. I don't see any reason, from the day, Chat GPT 3.5 came out, I was immediate like, look, this is graduate school. You should start using this immediately, because how can you not, what's the benefit of doing things with one hand tied behind your back? Yes, I mean, there are training without the use of the AI is a good story, but we're kind of short on time, so let's not pretend. So let's see, why would I take the log? Now, natural log is log base C. We always write log. Okay, in case in high school you may have seen it ln. Why would I take the log of a data set when doing statistics or other data analysis? I presume my Chat GPT is showing up on your screen, yes or no?
No.
Okay, that's well, anyway, that's my question. Let me see if I can I stop sharing it, will probably. Anyway, you can type it into your LLM, and I'll type it into mine. It's a common transformation used to handle specific structural issues in data, and specifically the one that's comes up is right skewed data. Taking the log pulls those extreme values towards the center, makes it closer to a normal distribution, as promised. Okay, so I think I have to do, let me just reset my share. If I set my share to share my screen, okay, share my entire screen. Here we go. Share. Okay, now when I share my tab, you'll see that. And when I share my Gemini, now you see my Gemini, yes? Okay, good.
Yes.
So anyway, this answer comes, which is what I had told you. And then there are other reasons potentially interesting. This goes to your hypothesis, Cliff, which actually does have a validity stabilizing variance. Standard linear models assume that the spread or variance of your errors is constant across all levels of your data. However, in many data sets, the variance increases as the mean increases. That is, as people get richer, the variation in their spending habits grow in terms of dollars, right? So if I'm making if we have a bunch of people making $100,000, maybe before tax, maybe some of them spend, maybe the range of how much they spend in a given year is $10,000. Whereas if they make $1 million, the variance could be on the order of 100,000, even just proportionally, right? So proportionally, they're the same, but 100,000 is a lot bigger number. So stabilizing the variance, aka homoscedasticity. If you've never seen this word before, homo, of course, means same, and skedasticity means variance, essentially. So something is homoskedastic. That means it's got a variance that's the same across all values. If it's heteroskedastic, that means that the variance varies as the data varies. One of the requirements of doing traditional linear regression is you prefer that your residual values, your errors, be homoskedastic. That is, if I input a 5 into my model, I want the range of estimates to be similar as when I input a 25 into the model. I don't want the range of errors to grow big. When that's not the case, good statistical methods will often ask you to take the log, for example. There are a few other transformations we can do. Okay, so that's probably why exponential the log has been taken here. All right, so what happened here, and it tells the story. Well, this next slide just explains the split. You can see there's only two sides. So how does it make the decision? Well, here's the goal. The goal is that when we got to this top node, we had two decisions to make. One of which was, which variable should I split on? Years of experience or number of hits in the prior year. And in this case, we said, let's just say I'm going to split on years. If I choose to split on years, then the question becomes, well, how many years should I split on? So going back to our data here, our picture, you can kind of see, if I'm going to split on years, you can see that by splitting right here at the 5-year mark, we get a pretty good, homogeneity of the data. The data all has the same color by the scheme here. And all the data on the other side of the split also has the kind of good data. Now, we don't visually make this decision. The goal will be to have the model decide, first of all, if I split on years, what's my best choice? Okay, it comes up with 4.5. If I were to split on hits, maybe it decides that the best place to split on hits is like this number 130 or something. And then it will compare, how does splitting on hits improve my understanding of the data? How does my splitting on years improve my understanding of the data? And then the question you should be asking yourself, well, what do you mean by how do I improve my understanding, quote unquote, of the data? Okay, well, that's going to be the next step in the discussion here, which is, what are the criterion for evaluating the goodness of splitting on years, A, versus splitting on hits, B, or splitting on years at 4.5 as opposed to 5 or 6 or 7. Okay, and then, one second here. So let me just jump ahead to that. We'll come back to this for a second. So the answer is cooked in here on this slide. So you obviously will want to read these slides by yourself. We'll spend about half the class or so going through some of these slides, and then we'll spend the second half of the class on Python notebooks from the other textbook that we've been reviewing. So what this says, this is an exercise in notation, first of all. So the goal here you might recognize is you're going to have a yi, which is the true value of your data, and you're going to have a y hat, which is the predicted value for that yi. And we're taking the square error. So again, this is we're we're doing a least squares error. And then the only question is, what are these two summations? The first one says, take every I that's in region J. We'll see that in a second. All right, so let's go take a look at what the regions are. So the regions are these boxes, which is that the splits that we've done is first we split on years. So we split all of the dots into two places. Either you're left of 4.5, you don't have that much experience, or you're right of 4.5. And notice again, the 5 years actually gets split out. You can kind of see that the model did a good choice. If we split at 5, we get this confusion. There's some blue and greens versus some yellows. But if we split at 4.5, almost all of the data include nothing that's either yellow or red, the high valued thing. So that's actually a good, it doesn't split on 5, it splits on 4.5. This is my Mac without a mouse. Okay, apologize for that. And then the second split is we're going to split on 117.5 hits. So let's go take a look just to see if that conforms with what we might do by eyeball, right? So by eyeball, we can see once we've decided to split essentially everything from 5 over, we can see that down here there's a lot of blue and green. The less successful players are being paid less. And up here, the more successful players are. And you can kind of make a good argument to say, well, 117, that's about here, right? Now, of course, the whole point of doing machine learning, if this was the full question of how do you solve this problem, you could probably come up with a similar set of rectangles. I have to remember 3 fingers moves the window, 2 fingers moves the slides. You could come up with a similar split on your own. If I were to put these colors back into the graph, it's not inconceivable that you might come up with these same 3 splits. You would still probably want to have that error minimization concept in line. And the error minimization. So now what we're going to say is over every dot that's in box 1, region 2, and region 3. So summing over, so RJ in this case is going to be region 1, region 2, and region 3. Take every I that happens to occur in region J. So just give them some numbers. Set data point 1. Well, actually, let's say I think there's 350 data points in this. So the I's are really, the global I is like 1 to 350. But the local I's are, there's 100 samples in the first box. There's 125 samples in the second box and 125 samples, let's say, in the third box. So we take all of those Y's and we compare it to the Y hat that's associated with region J. And notice since we only had 3 boxes, region 1, region 2, region J equals 3, there's only going to be 3 summations in the outside sum, which means there's only 3 values of Y hat. And that goes back to what we said the model would do, which is once you get this partition of the input space into these 3 spaces, if you get a new player who falls into region 1, your prediction is going to be that that player is paid the average of the region 1 players. And if it's region 2, he's going to get the average of region 2, because we're talking about Major League Baseball, okay? And region 3, we're going to get the salary of region 3, which, as we said, would be E to the 5, E to the 6, and E to the 7, essentially. And that's not a very refined model. There's only 3 possible salaries. The obvious next question would be, could we do better? And the answer would be, well, yes. Once we expand behind only using 2 of the pieces of data, if we only had hits and years, maybe that's the best we can do. I will point out that when we, even though we stopped our tree here, right, we could have done the following. we could have done years 4.5 up here. When we got down to this node, we could have chosen to split again on years or split on hits. We could split this left tree by hits, just like we split this right tree. So I'm pointing out that, these trees can go down to many levels if we think it's a better model. What would the risk be of having many different levels in this tree? This is binary. Go ahead, Cliff. Okay. Yeah, I would go a little further. Let's make it more general. What's always the risk of pushing a machine learning model or any statistical model too far? Asking it. That's right. If you look, we could split this tree potentially into 350 leaves. So these things at the bottom are called the leaves. So this is a tree. Now, obviously, it's an upside down tree because the root is at the top and the leaves are at the bottom, much like computer science trees for doing a various algorithm computer science are also upside down trees. But the idea is, you could split this tree up to 350 times based on the individual nuances of every single player. And then your tree, your performance would be excellent, right? What would your mean squared error be if you had as many leaves as you have inputs, data points? Your mean squared error should be what number? No, close, but the other number that you could only possibly guess. Right, it'd have to be, you could push your model to get every single player right. And, maybe not with just two data points, because there's clearly people with the same level of experience. And even like this purple dot in the middle there is being paid less than these two blue dots. So maybe there's an overlap that makes this a little bit inconsistent. But in theory, you could get each dot to be its own leaf on the tree, and you'd be great on this tree. But as Cliff said, we'd be overfitting. We'd be matching the data, and then when new samples came in, and how do we deal with overfitting issues in general? We typically do something like say, you know what I'm going to do? I'm going to pick, half of these points at random, or I'm going to do something like I'm going to split the data set into 80% of the points randomly selected will be my training data. 10% of the points will be used for validation, and then 10% will be used for testing. And that 80-10 split, sometimes called the training validation test split. At first, the book introduces you to training and test split, which just says I'm going to train my model on, let's say, 80% of the data and see how good it does on the 20% of the data I held out. But then we also do other things like in order to fit the 80% well, I keep 10% in the background as to fit the hyperparameters of the model. How many trees, how many clusters should I have in my k-means clustering algorithm? Or how many, well, let's just use that for now. In the case of the trees, how many splits should I make before I stop? You could use that extra 10% as a way to make those decisions. And then once we've figured out what is the best we can do, having used our 10% to train our 80%, now we have our final model. And then and only then we look at the test data and we say, okay, how good do I think this model will do in the wild? And the test data is our one clue whether or not we've got a model that has good predictive properties. And we would assume that if we've taken 80% of the data and fine-tuned it with our model using extra 10% of the data to see how to fine-tune the model built on the 80, we fully anticipate that when we go to that last 10%, it's not going to be as good as when we fit the data, but we're hoping that the performance doesn't decay that badly. Okay, we'll see some graphs that bring this point out. Okay, so so we talked about the tree. The regions are called terminal. No, let's just skip that for now. You can read through these details on your own. And the book, like I say, is a great book. In fact, I learned something interesting that the authors of our book. Let's just go back to ISL. I was looking into the book for some other purposes. I was looking at some other stuff recently, And where's their pictures here? I guess the pictures are at the bottom, I think. Yeah. So the original R book, I think version one only had three authors. I think Daniela Witten was an edition for the second. I think she joined in the second edition. So these four people definitely wrote the second edition. You can see they're all professors of stats. I think these two guys are the original authors of the more advanced mathematical book. I mean, it's all the same methods, but they prove a lot of the mathematics in their elements of statistical learning. That one came out in 1999. Then they've been at Stanford forever. I think these two people maybe both went through Stanford to probably in the yeah, Daniela Witten was a graduate student. That's right, and I think even yeah, he might have also been at Stanford, but I think he was one of the original authors. So maybe he knows the other two authors from the original authors of the L of the introduction as opposed to the elements. And I think, well, no, the guy at the bottom. We're going to go down him in a second, right? So I think Daniela Witten joined. She was a grad student, and they said, let's make a second edition and maybe make it better. And then this guy joined for. For the Python edition. He's a professor of statistics at Stanford. And if I'm not mistaken, this guy, Tib Shirani, has a son. I didn't verify that, but it's hard to believe he's not the same, who got his PhD thesis under Jonathan Taylor. So, as usual, who doesn't hurt in this world. And, having your father being a brilliant statistician is one of the possible suggestions that you might end up being a academic statistician as well. Just a little color point there. Okay, so the details of the tree building process. We divide the predictor space, that is the set of possible values for the x's, which are the features of your model, into j distinct and non-overlapping regions, R1 through Rj. And then for every observation that eventually falls into region Rj, this means observations we haven't looked at yet, we make the same prediction, which is simply the mean of the response values for the training observation. So you do get a lot out of reading. You start to talk the lingo of the scientist, whether it be a machine learning scientist or a statistics or mathematician, right? And there is jargon. There's often criticism that jargon doesn't translate well to the public, but when you're trying to embrace the mental set, I don't have to tell you as master's students, learning the jargon is good. So this just says everybody in R1 will be given that same salary. And we can see, you can kind of estimate where well, you can't estimate where the salary is here because we don't have the colors, right? But you get the idea. And the point is, once you train your model, you've now got a model that you can use to predict new cases. Now, in the case of this model, they talk about, so in theory, what you'd like to do. Now, keep in mind, in this simple version of the model, we're only using two features, hits and years. We'll see that I think the original data set, the baseball players' salary data set, has maybe 10 or 13 features. So the easy eyeball visualization that we could do when things were only in two dimensions and we've got the color giving us a third dimension, right? That's kind of a nice trick that data scientists do, right? Which is I can see three dimensions. You can see it, right? Lay it on the graph. I can see the blues and the green and the greens cluster to the left, and the yellows and the reds start getting you up into the right quadrant. And white quadrant does mean success. By the way, the thing that keeps prices low, salaries low in the beginning, is that when a player comes into the league, there's a minimum salary that people are paid in accordance to the contract with the Major League Baseball, and they're not allowed to. I don't have all the details, but they're not allowed to auction themselves off to the highest bidder until they, I think, have that 4 years of experience. So I think after 4 years, if they haven't signed a longer contract, they are free to negotiate with anybody who wants to hire them, and then obviously drives their salaries up if they've been successful. And if their salaries are not, and if they're not that good, there's a decent chance that they drop out of the data set and they don't play baseball anymore. Consequently, even over here, the lesser successful on the hit side still are getting the lighter green moving toward yellow salaries by virtue of having this is only, again, and the yellow and the colors only, the hits only reflects last year. So they may have signed a contract 3 years ago when their hits were a lot higher, and even though they're not doing as well now, you'd have to. This is one good thing that I do like about the machine learning blueprints for finance book is he does have a good 7-part strategy for analyzing your data. And he talks about it in the book, and then he does it in every notebook. He shows you here's how the 7 parts play out. And one part that every data science book will tell you, and machine learning is certainly an outgrowth. Data science is certainly a valuable component of machine learning. There's more to data science than just machine learning, but is that you need to look at your data. You need to understand your data and make sense. And your data is going to be messy. He talks in the book. In fact, we'll see in the second notebook that we have tonight. He talks about how do you deal with a messy data set. How do you not every data set is something that's been canned by some academic or cleaned by some Kaggle competition to let you get good answers. In the real world, data is messy, and just because it's messy doesn't mean that it's useless. It just means that you have to work a little harder to bring information out. And we'll talk about that, like I say, in the second notebook that we look at tonight. Okay, so we talk about the tree building process, and then we did talk about. It's worth pointing out, that first split on years is what we call what's taking a top-down greedy approach. So we just say, look, I'm going to look at years, I'm going to look at hits, and for years I'm going to consider the choices. For hits, I'm going to consider the choices, and whichever one gives me a better split by a criterion we're going to see in a second, that's the one I'm going to pick. Okay. And actually, we know the criterion is, could we, get better mean squared error? And this is called the greedy approach. Many of these computationally, ideally, let's say we go back to our case of having 13 trees. The first split is an easy split, right? It divides us into this region and this region. But, a question you might ask would be, well, what happened if we had just split the region over here? And, if we made a much more complex division of this, what would be the best possible choice? If we decided in advance that we were going to do 10 regions, let's say, could we make the best 10 choices? And if you think about what that means, we have to make, we have a tree which will have 2 to the 10, let's say, just to give us a rough order of magnitude, 2 to the 10 ways to divide these things in half, right? And we need to consider for each of those 2 to the 10 possibilities, what's the best path through the tree. And when we have that's if we only have 2 features, right? If we have 13 features and we decide we're going to go 10 layers deep, now we're talking that each one of the 10 splits, we have 13 choices. So we end up with 13 to the 10th power. I think I did that right. But suffice it to say, we'll just take it's either 10 to the 13th to 13 to the 10. My brain is a little foggy right now. The reality is, it is computationally unfeasible. This is an example of what's known in computer science as an NP complete problem, which means that we don't think we can complete this in polynomial time. Polynomial time, the basic rule of computers, if you have a matrix, n squared problem, easy to solve with a modern computer. If you have a 3-dimensional problem, a cube of matrices, n cube problems also reasonably easy to solve in computer science. But once you get to the 4th power or the 5th power of complexity, you begin to get to the point where on a large data set, you cannot expect to solve it, because pretty soon the number of possible answers becomes greater than the number of atoms in the universe. And that's sort of like kind of a limit on what we could possibly compute. Top-down greedy approaches say, okay, look, I'm just going to do the best I can with this first split. aware of the fact that the split I make now might not really give me the best tree. It's just the best I can make with one split. Later splits, it might have made more sense for me to do something not so greedy on the first level. I might get a better overall tree, but we can't see that. So we do what's called greedy splitting. And then the book goes on to talk about different ways to fix the greedy split. And you'll see that if you go through these slides. I want to take you back down to choosing the what's the example that says in this case, you can see the baseball example expanded to more layers. So again, they split on 4.5 years, but when they get down to the second level, if they're on the left side, they consider the number of runs batted in, which is another measure of success for a baseball player, and then they consider putouts. And then they bring years back in, and they bring years back in over here. And the fact that they both happen to split on years versus 3.5 is a coincidence. It's not necessarily a guarantee that they would be the same. Okay. And now you can see over here we go hits and then the number of walks. All of these, you can think of them as measures of success or potentially measures of failure, depending on the context. And in this case, he ends up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 leaf nodes. And when you get a new player, you now get a more refined estimate of of how good the players. I think putouts would seem to me to mean the number of times that the player performed a successful defensive play. I would suspect that successful defensive plays would get paid more. So I think that less than is probably a typographical error. You can see that less than 3 years, you get paid less, 4.6 than 5.1. I think if you do more putouts, you're probably going to get paid more. So I think that's probably an error. And in fact, you even see that this thing here is enough to generally speaking, RBI is, it without a doubt is a measure of success in baseball. So getting lower number of RBI would suggest you're going to be paid less and this would be paid more. But you can see this 5.487 is actually enough to make you get more money than someone who had more RBIs than you. So this is probably almost certainly a typo. And similarly down here. So anyway, you can see you get different numbers. And this just goes to, again, you see an example in a book. We don't have a lot of information on the data set. We could find it if we were motivated, but you would ask these questions, right? Part of what I'm trying to inculcate in you here is that, look, in this class, we only have 13 weeks. Professor McDonald gave, in the focus in the first half of the class is really a lot, the topics are linear regression and logistic regression, but a lot of the thinking is about how does a data scientist apply models in a way that enables them to assess the quality of their models. How do they make their decision? In the second half of the class, we run through more models. We looked at PCA, we looked at k-means clustering, we looked at a few other methods last week. We looked at, 2 weeks ago, we looked at reinforcement learning. Only a quick story there. A lot of these reinforcement learning, for example, is typically a full course in a computer science department. But when it's a full course, you're expected to master like every aspect, including probably writing the code yourself in many cases. This is a survey course, but the idea is that you learn about these methods, and when you start to think that you have one that might be useful, you really need to obviously dig into it and find its shortcomings. I'm not, this is not a CS program, right? In fact, I wouldn't even think to write any of these codes for myself. sklearn wrote these codes 20 years ago. People have been improving them and making sure that they're valid for 25 years. I would expect that I'm never going to build a random forest model that's better than the ones I can get from Conda or PIP. So consequently, but you do need to ask questions and understand, what do the models tell me and how do I use this? And certainly once you have something, in my case, I work in financial services, And part of what we use machine learning models for is making predictions as to what are good investments and what are bad investments. Once you have a model that you think is giving you a good prediction, and how do I know it's making good prediction? Well, that's what the first half of the class was about, is how do you evaluate the quality of your outputs, right? Once I have a model that I think makes a good prediction, I really need to dig in a little bit deeper and make sure that what I think the model is doing is in fact what it's doing, and that what I think is happening is appropriate to the task at hand. You want to decide these things before either A, you go to your boss and say, hey, look at this great model I have, or B, you put money into your model and you say, okay, let's trade with this, or let's roll out a new initiative on our website to attract more customers, or let's put into let's go give the FBI advice on how they should know who is the terrorist threat at this rally that's taking place on the mall, right? These things are all things that you have to really think carefully through, and you will make mistakes, but hopefully you minimize your possibility of making mistakes. They talk about so how do you decide to in the case of regression, we already talked about each of these nodes. The selection between why were RBI and hits selected was because if you picked RBIs, all of the data in this RBI subset has a certain error at this point of the split, a mean squared error, right? You take all of the data points that will fall into this category, compare the prediction for this category, which is the mean versus themselves, minimize that square. And what's the best choice of RBI? It turns out the number is 60.5. Okay. And RBIs will probably range from something like 20 to 100. So you can split that's only 100 splits on a modern computer for 350 data points, of which only half are falling over here. That's not too many data points, right? But you get a prediction, right? And then similarly, you ended up with hits over here. And you said, okay, like of all of the people who have more than 4.5 years experience, what's my best choice? Well, I could split them on hits, or I could split them on RBI, or I could split them on walks, or I could split them on runs, or I could even split them again on years. Which one of those is the best choice given that I've given the optimal split point? And in this case, it was, and again, what's optimal mean? The least squared error for all of the, keep in mind, at this point, we split everything into two possible categories. Let's just say 100 go left and 250 go to the right. Okay, each of these 100 are going to have, you take the mean of these 100, it's going to be 100, let's say it's 148,000, right? The answer we saw up below. Well, each one of those is going to have an error to the 148. You take the square of that error, and that's your choice, right? If you move the years to 5.5, that mean squared error between this side and this side, because you have to do both sides, will go up, and that's how they settle on this model. If you think about it, if you go through the slides and go through the model, it should become pretty clear. What we do down here is the question: how big should the trees be? So again, good graphs can tell you a lot of information. Every picture tells a story. So this is your first look at this graph. What do you think this tells you about the best choice for the size of the tree?
I think the second tree, because at that point, all the points like the training set, cross validation, and test are getting closer.
Okay, so let's see what we've got here. We've got the test set, the training set, and the cross validation set. Okay, right. So the idea would be you pick a number of the tree size, I think, means the number of splits. So the number of leaf nodes, as it were. We did see 12 in the one we just looked at. This one only shows 10. So the black says, look, the black says more trees is good, right? And that makes sense. The more splits you make, the more the more you travel down that tree, if you're, like we said, if you make enough splits, you'll end up with every player's got their own node that describes that player exactly and has his salary exactly, and his salary will be right. So your mean squared error will be 0. So if you run this thing to 350, this will drop down to 0. right? And this is the mean squared error in the logarithm of the price. So what's the cross validation set? You can see what happens, and this is to your answer. Hold on a second. The cross validation set, as you say, look, the cross validation goes down. Now, look, so what does cross validation mean? So you're training on 80% of the data. You're either cross validating on 10%, or we're doing a kind of a split into 5 data sets where we train on 4 and test on the 5th, train on the other 4, test on the last 5th. We divide it into 5 sets: A, B, C, D, E, right? We train on A, B, C, D, validate on E, train on A, C, D, E, validate on B, train on A, C, D, A, B, C, E, validate on D, and so on. You get the idea. Leave one out, validation, right? And what we're getting in reports is if we take 2 trees, we can see that the cross-validation error is close to the error here. And then at this point, the cross-validation error, this is important, right? It's still dropping, okay? Which kind of tells me I might go for these 3 trees right here. And then here, the tree is getting better, but the cross validation error is slightly higher. Okay, but it's not bad. And finally, we get down here and we see that the training is improving, but the cross validation is getting better, which begins to suggest perhaps this is overfitting. And finally, in comparison, we take the last 10% of the data, which is, so keep in mind how this works is we let's say right here, we train on 4 trees on however many splits we put our data into, like leave one out, cross validation. It's often, we 20% of the time, like we just said. And, but once we've decided that once we have this error message, we then go and fit the best possible tree on not just the training data, but we fit it on all of the data. So in other words, let's just say the training data is 80% and the test data is 20%, right? So now the training data is 80%, but we split it up into 5 pieces. Each one's worth 16. So the cross validation is on each of those 16%. Hopefully you understand this, but if you don't, you can ask me about it. Okay. But once we decide we're going to use 4, we then use all 80%, and then we see how did we do on the 20% that's left over. And we see here at the same time that the cross validation scores start to deviate significantly from the training scores. Also, the test case starts to vary. Okay, and so like you say, somewhere in here. So over here, I think we're still getting improvement on the on the cross validation at this point. So I would certainly get to at least 3. Whether or not to continue to 4, we are starting to lose information. So that's a good suggestion that maybe 4 is not the best. 4 is the best place to stop. So I probably would stop at 3. And at 3, you can see in this particular case, now it's sort of random how well the test data is. There's no reason why this test data has to be an interesting question. I guess, so here's something to think about. This is a question you ask yourself looking at this data. Why is it that the cross-validation data is uniformly worse than the performance on the test data? Anybody have a hypothesis for that? Oh, by the way, notice they're also giving us tick marks, which really show us that there's a sort of an error bar around this information, which is, I'm not going to explain right now, but it's good to ask yourself, what are those error bars? Well, actually, let's ask that question first. So we have 2 questions on the table. Why is it that the orange tends to be better than the green? Okay, what is it that is, what phenomenon is driving that, or what part of the process that I just described is right? And secondly, what are these little marks usually represent when you see like a box and whisker plot? In a box and whisker plot, it tends to be 25, the median, 75, and the data. I don't think that's what these are in this case. I suspect. Yeah, it seems like it's somehow, it should be linked to the standard deviation of the data inside the samples, right? So we have the mean squared error that we're minimizing, but then over the whole data set, we have a standard deviation, we have a variance, right? Which is, we have an, we have every data points gets predicted. Yeah, so it's kind of an interesting question to me. I admit I don't have the answer positive in my head, but it's probably related to variance. Okay, second question: why is the orange inside the green? What is it about so my suggestion was that we used 80% for training, and we split it into 64 and 16 of cross validation 5 different times, right? That's what we did. And what we're showing here is that the training error was on the order of 0.3 here, whereas the validation on the 5 sets individually was about 0.42. What is it that makes the orange thing do better than the green thing? I'll give you my answer, which is that, as I said, after we decide that we're going to use 4 trees, we then fit the entire data set, all 80%, I should say. So when we're doing the cross validation, we're using 64% to fit the 16%, 5 times, and that gives us our average error on the 5 different folds of that k-fold, cross validation. But when we finally say, okay, I'm using 4, I use all 80% of the data to fit on the 4, and then I use that 80% to predict the remaining 20% that was left out in the test phase. So I think that's why the test data are better, right? Because there's 80% of the original data set is informing the decision on the other 20% of the data, whereas in the validation, only 64% of the data is being used to forecast the 16% of the data. That's kind of the story there. So these are good questions to ask yourself as you move through this thing. We can use these for classification, and when we do classification, once we get the tree, we predict that each observation belongs to the most commonly occurring class of training observations in the region. So in the case that I mentioned to you last week, just give me 1 second here. So in the case of, we talked about the Titanic last week, which is an interesting problem set on Kaggle. As you are aware, I believe the project for Professor McDonald is based on a Kaggle data set. And if you get serious about applying machine learning or data science to these types of problems, Kaggle is a repository of many tens or possibly hundreds at this point of problem sets that they provide data with. And they also have a lively discussion from the different people that participate in Kaggle over the years about what makes for a good model and what makes a bad model. So you can download plenty of free models and you can wade in. They have training sets, or what do they call them? Playgrounds, I guess. One of the most famous playground of which is there, were 1,300 passengers on the Titanic. Some number like 600 or so survived, based on 13 features or so that they give you in the data about each of the 1,300 passengers. Make a prediction whether this passenger survived or died in the boating accident. And that's a classification problem, because at the end of the day, your prediction is either 0 lived and 1 died, or vice versa. So in this case, so what you do is if you take your 13 features and somehow divide them up into a classification tree, was it a man or a woman? Was it an adult or a child? Were they in class 1, class 2, or class 3 of the tickets? Were they employees or passengers? Were they married or single? And how old were they? Were they above 50 or below 50 in age, and so on? And based on that, you build your classification tree. And how do you kind of determine whether your tree is any good? Well, you probably do something like, you fit your tree to 80% of the data, and you see how it does on 20% of the data. Now, it's a pretty small data set, only 1,300 points. So you'll find the Kaggle leaderboard is replete with thousands of people who have 100% accuracy on the model. But again, that doesn't get into how they do on an unseen data set. When you have the real Kaggle, that Kaggle also sponsors competitions, some of which are for fun, but many of which are for prizes, some of which are for significant financial prizes on even as much as $100,000. I think Kaggle got started in the aftermath of what was called the Netflix competition, which, if you don't know about it, was a prize offered by Netflix to whatever data science team could come up with a method that would improve their recommendation algorithm by just 10%. What that means is if I show Professor McDonald, if I send recommendations to Professor McDonald, 1,000 recommendations, and he watches 5 of the shows that I show him. Well, let's say he watches 30 of the shows that I show him, right? I would like my recommendation algorithm to be better, so that when I send him 1,000 next year, he watches 33 of my programs, 10% improvement. Turned out to be a pretty difficult problem to do. They had massive data sets even as early as 2006, and but it's, many teams competed for the $1 million Netflix prize, and eventually, large teams of data scientists from universities and other places all over the world would eventually partner up with other high performing teams to try to make ensemble models where each team's model would vote on what the answer was. And eventually, like 3 teams got to the 10% improvement level, almost like on the same day in 2006. I don't remember what happened to how they divided up the prize, but in the end, Netflix couldn't use the model because it was too complicated to really, produce the number of recommendations they want for the number of people. But it did spur a lot of interest in data science and machine learning algorithms applied to this type of recommendation system. And I think Kaggle probably started shortly after there as a place to sponsor competition. So if you go to Kaggle, well, we can do it right now, right? And my internet's a little slow. Let's just search for Titanic, for example. And you get the Titanic set, and you'll see, 191,000 results. This is one person's Python. You can see that the Titanic comes in a train data set and a test data set. So they do that for you. And they show you, look, passenger number 1 survived in class 3, Mr. Owen Harris Braun. He was a male, age 22. Did he have siblings, et cetera? A lot of different stuff here. And you can go and read how this person only did 57%. That was their best score. If we go to let's see, the benchmarks, let's see. Well, we'll go to competitions that are open now. These are the getting started. Machine learning from the Titanic, housing prices, spaceship Titanic. Okay, good. LLM classifications. That's clearly much more modern. Okay, and then here's one. The ARC prize paper track, $450,000 prize on the line. The Gemma for Good hackathon, 200,000. So you can poke in here and see how it's going. The ARC, there's a different ARC prize. Create an AI capable of fluid intelligence, and they give you the story. They give you some data, and here's the prizes. So all kinds of prizes. Okay. So people want to, wade into the world. You can see there's 4,000 entrants, 625 participants, 593 teams. There's a whole set of rules. This one lasts about 6 months. Started a month ago. It's got about 6 months to go. There's rules that say, you can combine your teams with other teams. Okay. There are 3 active competitions for ARC, and you can document your approach. Okay. So anyway, that's what Kaggle is. All right, back to our topic here. So the most commonly occurring class. So one way to so again, how do you make your splits? Like what's your metric for deciding to make your splits? The immediate answer is, and this is actually used in other machine learning algorithms, is your error rate. And the error rate in this case would be 100% minus the maximum error that you see. and we'd want to minimize this quantity. So, and then you need to read a little carefully where here, P hat MK. So, you got three things going on. P hat, okay, we know it's a predictor. MK represents the proportion of training observations in the mth region that are from the kth class. So go back to our two-dimensional plane where we had the baseball salary split into three rectangles. Those will be your regions, 1, 2, and 3. And in every region, we would make a prediction. In the case of the Titanic, would be this person lived or this person died. And the proportion of here, PMK, okay, a natural alternative is the training classification error rate, simply the fraction of the training observations that do not belong to the most common class. So the rule is, if you're looking at one of those rectangles from the baseball, but let's pretend those are Titanic divisions, rectangle 1 either has more living people or more survivors or more who perished. Rectangle 2 the same way, rectangle 3 the same way. Every person who falls into that rectangle, you predict whatever happened to most of the people in that rectangle, where most might only be 51%, right? What you would really like it if region 1 was 90% lived, 10% died. Region 2 was 10% lived, 90% died. Region 3 was 70-30. Because with those type of numbers, if the people in this region were 90-10, so for example, we might hypothesize that a woman from the upper class maybe had better access to the boats, or maybe it's the other way. Maybe the boats were put down in a way that the people who bought the cheaper tickets survived. The idea that more women survived than men, it would at least be it's probably true, first of all. And secondly, it probably also the movies would say, the men, women, and children get in the boats first, right? That's the way it is. But what you do is you say for every predictor in the mth region that are from the kth class. So, and the key, not really written here, is that do not belong, right? So we want to know, which is the class that has the worst case. This is a way of saying that was our classification error. It turns out that's not a great error anyway. Let's go back to this error here. So two errors that are used commonly, and this is something you also hear in other contexts. The Gini index is a concept that is not only part of machine learning, but it's also part of economics. And the second type of analysis is called the cross entropy, which was used, I believe, in your logistic regression model. Something similar to the cross entropy is used. Cross entropy is also a concept used in information theory. Excuse me. Let me get a little bit of water. I guess we're coming up on a break. So the key story that we want to emphasize is what is the Gini index and what makes it small. We want it to be small. So it tells us here that the Gini index will be small if all of the PMKs are close to either 0 or 1. So if they're close to 1, this will be 1, but this guy will be almost 0. If this guy is almost 0, then this guy will be almost this guy will be 1. So you're talking about summing a lot of numbers of the form 0 and 1. So every proportion is either going to be, the worst case predictor, right? So we've predicted, let's say we're looking at a division of the Titanic box into in some region 1, and we find out that we're right 70% of it. So there's only two classes, live and die, right? So the only question would be in region 1, if the prediction is you live, we'd want to know how many people died. And if that number is a big number, like 50%, let's say, but first of all, it has to be no more than 50%, right? Because if 51% died, that box would be predicting dying. The Gini index is a way of saying we'd like box 1 to be like 100% they lived, and 0% they died. Because then we know if they landed in that box, we're definitely going to predict that they lived. And similarly, some other box will hopefully tell us that they died. And even though these would not be ironclad proof that further examples would work, we'd feel more confident. If you take this a kind of a calculus problem you may have seen, what's the worst case? So we just said that the best case if is every p hat is either a 1 or a 0, because then we end up taking sum of lots of numbers that are almost 1 by lots of numbers that are almost 0. If that's the best case, what would be the worst case? If everything's a half, that's right. If this was always 50-50, because if p hat was almost 50%, right? And so let's say p hat's 51, at 1 minus p hat would be 49. So you'd have 0.51 times 0.49. It's basically 0.25 times 0.5, which is 0.25. There's a problem that you get in calculus 1. What's the best way to split two probabilities to maximize their product? P and Q, right? Turns out if P is 50% and Q is 50%, you get 0.50 times 0.50, 0.25. If you pick any other number besides 50-50, the product of those probabilities will be smaller. And that's kind of what the Gini takes this to extreme. Ideally, every p hat will be either 1 or 0. And then when you sum them all up, you've got a sum which is 0. That's the minimum of the Gini index. And for this reason, the Gini index is called a measure of the purity of the node. And when we're doing classification, we want purity. We want to land in a space where everybody who landed in that space has the same prediction, because then we feel confident that this person has all of the characteristics of class A. Therefore, we're going to predict class A. Okay. And cross entropy actually has a similar impact. Okay, before we take our break, which we'll do in a few minutes, there's a lot more to read here, but what I do want to get to is that in the remainder of this chapter, they talk about bootstrap aggregation, which I think I'll pass over for now. I want to get down to the concept of random forests. Okay. Hold on a second. Okay, so random forests, right? So random forests improve over bagged trees. So the fundamental concept is we build many trees. So instead of building one tree to decide how, remember the last baseball example we saw had 13 leaves. What we do instead is we say, you know what, I'm just going to build a tree. I'm only going to base it on one of the features. Let's say, so obviously we know from what we've seen before, we're probably going to base it on years of experience. Okay, that's good. But now, and that's all, I'm just going to split based on that and make a prediction. Well, now I want to split I want to build another tree. Well, if I'm only going to build a tree of one depth, and I always let years experience be one of my choices, I'm always going to pick on years experience. And all of my trees will be 100% correlated. So what I do instead, I say is, look, I've got 15 features in my feature space. And for the first tree, I'm only going to consider 5 of the possible features. I'll pick one of those 5, whichever one's the best, let's say, and I'll use that one. And then when it comes time to build tree number 2, I will pick another 5 of those at random, and whichever one's the best, I'll use that. And we build all these trees that only have 1 or 2 levels in the tree, and they all get a vote. And then at the end of so in many cases, the best single split tree, years of experience, will be important. But in other cases, some other feature, which seems pretty trivial, will be the best one of all anyway, especially if we randomize the data that we use to fit that tree. And by randomizing the data and randomizing the features that we let into the model, we create lots of decorrelated trees, which is they're not all going to vote the same way. Turns out, for reasons that they probably developed mathematically in their elements book, this generates a more robust algorithm for making predictions. And they typically use when building these trees, as it says here, each time a split is considered, a random selection of M predictors is chosen as split candidates from the full set of P predictors. So, like in my example, there were 15 data points on each baseball player. I'm only going to let 5 in for every split, and I might split twice. So, for the first split at the top of the tree, I pick from one of these 5. Then I have the two sides of the tree, and I pick 5 different ones for the left tree, 5 different ones for the right tree, and I split on that. And he tells you a rule of thumb is that we choose P to be the M to be the square root of P. So in our case, if we had 16 predictors, variables that define a baseball player's value to a team, we would take the square root of 16 and would only use 4. This is a rule of thumb that they do. Okay, and random forests get it in vote. And then the final and the ultimate result of random forest is they come up with one more concept, so-called boosting. And the boosting algorithm becomes the basis for what are known as gradient boosting machines, has something to do with the way boosting is done. And the algorithms, these algorithms get progressively more complicated. Basically, what the boosting algorithm does, it says, it fits one simple tree. Sometimes they even call them stumps if they only have one split. It says it fits a simple tree and sees how it does on all the data. And then the booster tries to fit the errors that the first tree had. Instead of trying to fit the answer correct, it just tries to fit the errors. Carries this out a bunch of times. This turned out for many years to be the most successful algorithm in Kaggle competitions outside of deep neural networks. And as we said, deep neural networks will work well on algorithms like pick the here's 10,000 pictures of objects from 1,000 categories, and I'm going to show your algorithm one of the pictures, and you have to tell me which of the categories it belongs to. In that case, 10,000 pictures is probably pretty good for getting your model to understand. If I gave you 100,000 pictures and told you how to sample, how to look at you look at what does a picture look like? A picture is 28 by 20. It's 760 by 760 pixels, and every pixel is got a red component, a green component, and a blue component. These are very large data sets, and algorithms can learn how to train on them. For those algorithms, visual acuity algorithms, deep neural networks turn out to be a good choice. But for data that doesn't have as much information, you can't fit such a complicated model. Gradient boosted machines turn out to be the winning model. Now, just at the end of this section here, they do talk about one more kind of model called and I would be remiss if I did not mention it, the Bayesian additive regression trees. And when you see the word Bayesian pop up near the end of a presentation, this is someone's about to tell you probably that you could do even better by using Bayesian methods. And it turns out you get to the end of this slide presentation, they say, yeah, the Bayesian method is actually even better than the gradient boosted machines. So you have your work cut out for you if you want to dive into this material and understand it better. We'll take a break for, let's say, 10 minutes. And after that, we'll look at some code that uses some of these algorithms to study some data. Okay, so we'll take a break and we'll start around, let's call it 7:35 or so. Oh, 8:35, sorry. Wrong time zone. And I'm going to stop sharing. I guess I should put some light in my room so I don't look so serial killer like. Good to see such an excellent turnout this evening. Onassis, I didn't have your name at the top of my head. I apologize when you made that insightful observation. And if not mistaken, I think Rami, you also weighed in on another occasion, which was good. I feel like I'm shouting into the void, but I check and I do see my microphone is certainly on.
Yeah, hello, Professor.
Hello.
Onassis.
Onassis.
Yeah,
Yes.
I got it later. Some of the mates helped me out. Initially, I was there, but I couldn't have the session.
Well, your observation I thought was excellent, and it's good.
Yeah.
Okay, let's see. Let's cook it. We have so I sent you two notebooks. And the reason why I send you the notebooks, of course, is that because the notebooks are a little old, they fail in some ways, depending on what version of Python we're running and what version of each of the libraries. So I went through them and fixed it. Now it used to be a fairly challenging task for me, which is why I had thought about going away from this book. It turns out with Gemini at my side, anytime a problem comes up, it's pretty good at fixing it. And even I fixed one problem. I think it's in this first notebook that caused another problem later on. And it turned out that Gemini could fix that for me too. So that was good to know. So in this first book, you do need to get the data. I couldn't send the data to you because they're fairly large. This one is downloads as a CSV from the author, but it's still like 63 megabytes, which typically the email systems will reject. And the other one comes down as a zip file, a gzip file, as it were. And that one's much larger. After it, let's see, I'm not sharing any screen yet. I'll do that in a second. After it comes after it's expanded, it is, let's see, PyCharm projects, week 8. Not week 8, week 7. Week 6. No, actually, that's the second uses the 63 megabytes, and the other one only uses 35 megabytes. Anyway, those tend to be too large for it. A lot of systems will reject things at 25 megabytes, I believe. I think Gmail, for example, does that. Okay, let me share my my screen with you. There you are, Onassis. Good to see your face.
Yeah. Good to see you too, Professor.
Yeah. So, reminder: we will have a last class next week. Professor McDonald will hopefully submit your projects by then to him. He will he'll extend that time if you want more time to work on it, but he'll talk about his answer. It's really about getting something done on your end than it is about being the best. I sent out a homework assignment. I'm not too worried about whether you do it or don't do it. I don't want. I'll be honest with you. I recommend you do it, but like I said, do Professor McDonald's first. That project's kind of the best part of the course. on your side. The project, the homework assignment I sent out, I explained, what do we learn from looking at this notebook where it talks about different methods of classifications? We find that, a pretty good explanation, pretty easy to understand what k-means clustering is. Not that hard to understand agglomerative clustering, although the details are not divulged, and you'll have to look those up if you want. And then the last kind, which was affinity clustering, which ultimately was slightly better than the other two methods, is much much worse explained. And if you want to learn about them, you have to go. And then we also said, well, what is this T-SNE diagram that he gave us? You might want to look up, what are they trying to do there? And then the final question, the book suggests that, XEC and DEC, whatever the two tickers might be a good candidate for a pairs algorithm. Well, how would you know? Well, you'll need to, as I suggested, take your 2018 data and run it. Use the data. He does give a data download notebook. It's not that easy, not that hard to download data from Yahoo and for stocks anyway. But the how so now let's just say you have this data from 2018 and now you've expanded it to 2025. How would I look about this data? Well, you could try to figure out how a pairs clustering trade would work, but would probably make more sense would be to upload the 7 years, let's say, or 10 years worth of data that you now have, and you say to Gemini, to your favorite language model. So I have this data, and it was suggested to me that based on data up until 2018, these two stocks would be good candidates for a pairs trading strategy. How do I go about that? And it would give you a nice little story that say, okay, well, here's what you do, here's what you're doing. You ultimately you want to tell, I want Python code, and then you just see whether it carries out, and it turns out to be good. Once you have that kind of rhythm down of here's two stocks and here's the data, you could certainly pick other suggested stocks in that index, or you might pick stocks that you think make a good pair: Coke and Pepsi, Apple and Microsoft, Google and Facebook, perhaps. Maybe these are good pair stocks. And what does the model say? But if you're going to go that route, you might go the whole route and say, okay, here's a basket of 20 stocks. I want to devise a pair trading strategy based on the data up until 2022, and then test it on a walk forward method going out to 2025. What do I do? Right? These are the kind of questions that you can ask the models, and it will come up with pretty good stories about what you should do. And it's up to you as the analyst to decide, is it telling me something that's correct? Because it will tell you stuff that's not correct on a regular basis, as you probably know. But if it makes mistakes and you realize why there's a mistake, you can talk to it and say, can you fix this? And this is the beauty, right? The fear, of course, in the job market, but also the beauty, which is that if you can describe what you want and you have knowledge about what would be ideal, you can get it to do it. And if it doesn't do it quite right the first time, it takes you a few minutes to understand what it did wrong, and then you say, I think you did this wrong, and boom, 30 seconds later, you got a whole new script that you can run and see whether it works. So this is the world we live in now. So we have to adapt to that reality. Okay, let me get a screen share going here. And let's just share the entire screen. Okay, don't look into the infinity window there. It's very dangerous, as you know. Okay, so fraud detection notebook. And, again, he's using his multi-part situation. In this case, the problem definition. I can make this a little bit bigger. Well, you should have the notebook in front of you, so I'll presume that you're capable of doing that, although having two things going at one time, unless you have multiple screens, is not that easy. I like it when I'm home. I have like two big screens and two little screens. It's a luxury, but c'est la vie. Okay, so in this case, 2013 credit card transactions by European cardholders. And the interesting thing, which you'll want to note right away, he doesn't talk about it until later in the notebook, but there's only 492 frauds out of 285,000, which is 0.17 of the transactions. So if your concern was purely that you be accurate, it would be hard to do better than just say every transaction is correct, right? Because you'll be right 99.828% of the time. Let's just call it 99.8% of the time, right? It's going to be pretty hard to build a model that's better than 99.82% correct, right? However, and that this is indicate so in the cases where a data set is highly unbalanced, most models, if you don't guide them, will just pick the one side that is got most of the cases, and it will have a high accuracy score, and that would be great if that's what you were measuring. But if you look at this data set, you understand the problem. What a credit card company really needs to do is they need to catch most of these 492 sets, right? So the real goal, or one of the real goals, is going to be, how do I catch the 492 frauds out of 300,000 transactions? The credit card company has a different, so you could say, of course, well, just reject every transaction, then there'll never be any fraud. The problem with that is obvious, that if you don't ever approve a credit transaction, you have no credit card business. So the goal will be to maximize the number of frauds that you get correctly identified while minimizing the number of good transactions that you reject. Now, if you're like me, you probably have credit card transactions rejected on a somewhat regular basis. When you're traveling, for example, or if you're making a large purchase of a TV, you'll get them. And sometimes I get them. Your credit card was attempted to be used to buy, $500 worth of Walmart gift cards. Was that you? And I was like, no, that was not me. They tend to reject those out of hand. Thieves, of course, are clever. If they happen to get a copy of your credit card number and your security code and maybe other personal information that might be required, they will try to make small transactions, like at a gas station or somewhere else. And if that one transaction goes through, they're going to be online buying TVs and computers, whatever the highest thing they can do before the credit card gets shut down. So it's a challenging game, and credit cards are a very profitable business, so people continue. And banks want to be in that business, but fraud detection is a big thing. And credit decisions are a big part of one branch of application of machine learning. There are other models that you can understand where there are other applications. Let's just the third work notebook in this unit, which we're not going to discuss, is Bitcoin price predictions from 2018, right? And it'll apply some of these models, and it will come up with a Bitcoin model, which in the end really isn't that great. And again, it's 2018, so it's probably no longer relevant here in 2026. But you understand that you understand two things. First of all, if people were able to come up with good models to predict tomorrow's prices in the S&P 500 or in the US bond market or whatever, they would not publish those models, because if I published a model that said, give me today's data and I'll tell you whether Apple will be up 1% tomorrow or down 1%, right? Well, eventually everybody would have, there's two different things. If I publish the model, everybody would immediately implement the model and then immediately begin trading Apple with knowledge of what tomorrow's price is going to be before it gets there. So it would push the model. So if Apple's trading at 100 and the model says Apple really should be trading at 101, that fact would start to come into focus in market participants who have this model by, let's say, 3:55 in the afternoon, right? And everybody would immediately start to buy Apple so that they could get that last $1 of Apple growth. And of course, as everybody starts to buy Apple, it will push Apple to 100.95 cents. It'll keep pushing it towards that true value that the model sees until there's no margin to be had in paying for Apple, because now you'll be overpaying versus the model, in which case you would start short selling it, and eventually they would all converge on that price. Secondly, even if somebody didn't publish this model, if it was that easy to predict what the true price of Apple is, as opposed to what the current price is, many smart people are looking to take advantage of this information, of the possibility of unlimited riches, right? And would, are spending a lot of time trying to understand how can I build a better price forecasting tool. And it turns out that this is essentially the foundation of what's known as the efficient market hypothesis, which is that the market will always land on a price, always being subject to the idiosyncrasies of human behavior, i.e., behavioral finance, right? But they will always, all of the information that tells you what the best price for Apple will be impounded in Apple's price by the end of the day. So in the one of the stories of the efficient market hypothesis is there's no benefit in things like doing charting or any other kind of technical analysis, because the idea is if there was any information there, everybody would see that information and immediately move the price in that direction. A even stronger form of the efficient market hypothesis says that even inside information can't be used to beat the market on average, because of the fact that once inside information enters the market, granted, now if you're the first person with the inside information, you're probably going to be able to take advantage of it. But as that inside information begins to get acted on by players in the market, then they will push the price of the security to the fair price. There are stories of people who do make money using advanced techniques, but they don't publish their techniques. So they do publish their results. So there do appear to be people who can make money above and beyond what would be predicted by the efficient market hypothesis. And in fact, well, there's another story for our finance class. Let's just move on. So we this is the problem. That's the definition. We load the Python packages. Now I've commented out the packages related to Keras. Keras is a machine learning library that was originally built. I don't know if it was originally built for this reason, but it was built to sit on top, among other things, to sit on top of TensorFlow, which was the first large deep neural network library. It was created by Google around 2015 or 2016. So deep neural network models started to have a significant role in machine learning applications in 2010, 2012, and so on. 2015 or thereabouts, certainly by 2017, Google had published a TensorFlow package, which just took all of the ideas that are super relevant to neural networks and put them into a convenient modeling package, which then they open sourced so that other people could use it. Eventually, Meta, Facebook, came out with a competitor called PyTorch, which in many ways has overtaken TensorFlow in the academic environment and also in many professional environments. They're both good models. You'll probably see them, but we're not going to cover deep neural networks in this class, other than as an aside. And consequently, most of I'm working on a Mac here, but if you try to install some of these models, they don't like the Mac GPU chip. So consequently, I've just factored them out. Just a note, so you can see all of the sklearn models. A lot of this we've seen: pre-processing for scaling data, model selection. You got train, test, k-fold validation, cross-validation, grid search, linear models. You got your logistic regression, your trees. This is what we're doing today. You got a decision tree classifier. There are other classifiers. We're not going to talk about them in general, but down at the bottom, we do get down here to the gradient boosting classifier and the random forest classifier, which are two of the models we talked. And these other models will run when we go through the notebook. Just of noteworthy, if you see this, to pickle something in this context is if you've been running a model for a long time, you will periodically pickle the results, the current state of the model, and save it to a file, a pickle file, .pkl. And then eventually you will or if you, let's say you finished training your model, so you've run a machine learning model that could take a couple of minutes on your machine or it could take days, you want to be able to save all that data. Pickle is one of the ways that data is taken from is put into binary format and compressed so that you can remember the information and load it when you want to reuse your model. Okay, loading the data. He talks about you don't get the full data set here. Now I switched to what did I do here? I don't think he switched that was him. He switched to credit card sample. If you go to Kaggle, you can get the full data and then read in credit card data, not the sample, and your results in the notebook would, in theory, match the results he presents in the in the book. And look at your data. One of the, if you read through the textbook, he talks about, as I said, it's a good book. It's not my recommended book for the semester. I like the notebooks, but I am recommending, if you're going to buy one book, to hold off on the Stephen Jansen book, which will come out in June, I'm told now. Okay, so a brief 2 months away, and you'll have 850 third edition pages packed with models and theory about how to be a data scientist approaching machine learning and finance. In this case, because these are credit card data, there's a lot of personal information baked into these things. So instead of getting descriptive names on the features, which might be, these are probably, judging by their sizes, all between -3 and +3. They've probably already been standardized in some way. I'm going to guess. There's actually a lot of data. We see in this case, there are 28 features, all of which are floating point. So they're numbers, they're not classification. There is one, there's an amount. The last thing is a class. Class is going to be whether this loan defaulted or not. We'll see what that means in a second. And then there are, I suppose these are timestamps. Okay, so there's 31 columns. I guess class must be like way over on the right. I don't think I can see it. Oh yeah, there we go. So this is the amount of the debt. Maybe it's in of the credit card transaction. I'm sorry. These are credit card transactions. And then the class, most of the class is going to be 0. These are good transactions. There's only going to be, like we saw, some small portion are bad. And then we do data set describe. And it kind of would have been nice had the class been over on the left here, but we could see more. So the min and the max are, this column is the min. So the min class is approved 0 or valid, not a fraud. The max is 1, which is a fraud. And the average of this is that this is your 0.17%, 002. So you have a lot, you have 300,000 of zeros average with, whatever it was, 500 ones, and that averages to 0.2% basically. Okay. So again, this is what are we doing here? Why am I doing this with you, right? Well, you have information in front of you. You have a notebook. The world is full of notebooks. How do I make sense of what's going on? How do I learn the lesson? I read the text. Okay, that's good. I got a story. Now I start looking at the data, and I need to think about what's going on here. There appear to be, I guess he was forced to limit himself to 100,000 rows. That's what he's telling us up above. Okay, and you see here in the subset that he picked, there's almost 100,000 not frauds and 223 frauds. And then he does some data visualization. He wants to see how these are histograms of the values of those data. So you might see this guy V6 maybe looks kind of normal. I mean, do these tell me that much? I don't know. But I will see things like this guy over here, V24, is skewed to the left. If had it been skewed to the right, we already know taking the logarithm would make it look more like V18, or I should say, V18. The classes, can't even see the 0 is 100%, the 1 is down here, right? This particular data has already been cleaned, so there's no need to clean it. And he does a feature selection. Although some of the features are relevant, feature selection is not given significant preference. Okay, we go through this. Now let's evaluate the models. So he divides himself. He uses the sklearn train test split algorithm to take the X's, which are your data. And notice how he does this. And again, so look, you can get Gemini to do a lot of this stuff for you. Gemini against my LLM, but you can use GPT, whatever user. You can get it to do a lot of this stuff for you. And splitting the data, all it says is my predictor, the thing the target variable, this is a supervised learning algorithm, we're back into supervised learning, is the class, which is going to either be fraud or not fraud. And the set of predictors is all of the columns which are not equal to class. You can, like I say, a year ago or 2 years ago, for me to understand what this thing does exactly would require two things. One of which is I could play around with the code and see how changing it a little bit changes it, or I could see what does the data set look like. Well, I know what it looks like, all those X's. What do I end up with X? So let's just say I think my notebook is already, I haven't run it yet, so let's just I'll let this whip away while it's let's just run it from here. Okay, so I've done this train test split. I'll just pop a box up over here. I can say, hey, what does this X look like? And X, I don't know. I do know that data set is a data frame because it was read. We used pandas to read the CSV in. And if you take a subset of a data frame, you still get a data frame. We could verify that, right? What is my object? It's a data frame. Okay, that's good. So since it's a data frame, I can apply the head method to it. And no surprise, it's the original data set, except now it's got these 28 features and it's got the amount, which has not been scaled in any way, shape, or form. And it dropped the class, right? And we can look at what is the Y. And if I put, Y, what's the type of Y? Well, interesting question. What is the type of Y? Let's just take a look. Y is take data set and grab the column class. This is probably going to be a series, okay, which is one column of a data frame tends to be a series. You could make it into a class if you wanted to, but you can see a series looks a little bit differently. It's got just the index, which was from 0 to 100,000, and then it's got the result, which is either 0 or 1. We know it's mostly 0, okay? And then so he gets the data, and what he does, right? So I've got my trainings, and then he says, look, pass X and Y in, and use 20% as my validation size. So keep 20% of the data on the side, and then set the random state equal to seed. If you run these notebooks without, a lot of these notebooks will fail on this. This particular one does not care. The idea of a seed is that train test split uses randomization to decide which, if I'm going to split 80%, 20%, which 80% do I take? And it uses randomization. So if I were to run this model 2 times in a row, I might get different answers. That's the purpose of the seed. This says in your random model, use the same seed every time, then at least the results will be reproducible. That way, down below, when I start making changes to the model, I know that my changes are having effect, not because of the way I did the split, but because of the way I made the change. Now, the one thing that's not talked about here is the concept of stratified sampling, which is ideally we would like our data to include examples from the fraud case as well as from the not fraud case. Now, if you think about it, if you take 20% of the examples and put them on the side, will you, I mean, on average, will you get, where's the numbers here? On average, you'll get 20% of this in the one set and 20% and 80% in the other set. So 80% of 200 is 160. So you get like 170 in the training, and you get the other 50 in the test. Ideally, right? But it's possible, just due to the nature of the randomization, you might get very few examples of the fraud case in your training set, which would then give your model a problem. So a approach called stratified sampling often will apply the 80-20 split to the fraud examples and the not fraud examples separately, so that your training set has the correct proportion of fraud and not fraud, as does your test set. Okay. And then he goes ahead here, and you can, of course, review the notebooks in your own time. he starts out by doing some basic, what he calls basic classification algorithm. So logistic regression, of course, is your first algorithm. It does just a 0, 1. Linear discriminant analysis was an improvement on that. K-nearest neighbors classifier. So we did K-means clustering, which is an unsupervised algorithm. K-nearest neighbors works similarly. It takes the concept of centroids, just like we had in K-means clustering, and if we use our XY plane as an example, right, where there's two features, the Y is the the standard deviation, and the X-axis is the variance. And every data point can be put into this XY plane, the mean standard deviation plane. But now these numbers have classes that, maybe like all of the ones with high volatility and high returns are tech stocks, low volatility and low returns are utilities. So there are known answers to these problems. And the K-nearest neighbors uses a algorithm to, you may have covered that with Professor McDonald, actually. Did you? K-nearest neighbors? Yay, nay? Hard. Okay, good. So I'll leave that at that. So anyway, he does some basic algorithm. There were a few other basic algorithms which I took out of this. I don't know why I took them out. I think because these two guys are kind of slow. Let's at least throw the random forest in. Okay. So all this does is it's just building up a list of models, and look at, it's just building a list, right? That's all. This is a simple list in Python, and you can append an element to the list. And what are these elements? These are just, on the one hand, it's, what do you call something in Python which starts with parentheses, ends with parentheses, separated by a comma? So in other words, and again, this is like, let's get the type of this object. Anybody know? You can say it while I'm typing. Oh, I didn't put enough parentheses. What did I miss here? Yep. Okay, so let's just, I'm taking the type, which is a Python method, which will tell me the type of this object. So what do you call this object in the middle here? It starts with the parentheses and it ends with the parentheses. And it's got two things, one of which happens to be a string, one of which is a method. It's actually the constructor of sklearn model for logistic regression. And the magic answer is it's a tuple, right? It just consists of two objects, right? What is the type of 1, 2? It's also, oops, I forgot to hit shift enter. I left out another parentheses again. Okay, so it's a type. It's also a tuple. But what's the type of? So notice type is a function. I'm going to give it the type of this 2, 3, 4, enclosed in square brackets, right? And that's a list, right? What's the type of? What if I put it in? Okay, here's a trick question for you. What is the type of this guy? It's let's find out. That's a set, right? One more. What's the type of this guy? 1 maps to A. Let's call it A. And 2 maps to B. So what 2 maps to B? So I've got a set of pairs, as it were. The first element happens to be a number. And let's just call this, let's just say D equals this. Okay. It doesn't do anything. What if I ask it for the type of D? Anybody know what the type of D is? It's a set of key value pairs, right? Which is one of the most useful objects in a lot of computing and data science. It's a dictionary, right? It's, if I could reverse it as well, person A has phone number 1, 2, 3. I don't need to have them be identical. I'll show that. In fact, person B has phone number 2, 3, 4, and 175 happens to be a letter. Okay. It's doesn't like that. Oh, it's because I put a semicolon there. Okay. Still a dictionary, but now I can say what's print print D of A. The argument here goes like this, right? I got balance that thing, and then I'm also going to print. I won't even put print. I'll just put D of 175. So D of A, you can see the dictionary. You give it the key A, it looks up A, it finds 123. You give it the key 175, and it brings back the string C. Now, most dictionaries don't make sense where the keys can be different types and the outputs can be different types, but you can do it. So these are types, right? So all this is doing, we're building a list and we're appending models, right? So if I come over here, I've already run this cell, and I say, what's the type of models? And it's just a list. And what's the type of model number one? It's a tuple. What is model number one? It's this tuple. And it tells me it's an array. No, I don't think I want that. I guess I want, oh no, I want models one. I don't know what model is. Models get used down below. Model one is a tuple consisting of the string LDA and the constructor to the linear discriminant analysis function. So what he does in here is he makes a list for result, he makes a list for names, and he runs the models using k-fold cross validation. I only have 4 of them here because I didn't have which one did I just added random forest. Let's take a look at what we get here. We run this, and I guess I probably killed a few of them because they take too long to run. These are pretty fast. My computer is pretty fast in general. It's a MacBook from last year, but you can see it kind of bogs down on model number 4, which is a classification and regression tree. So this is a pretty big data set. It's got 28 features and it's got 100,000 examples. You could do a lot of splitting on that tree before your overfitting detector says, hey, you know what, maybe you ought to back it up a little bit. And random forest classifier probably take a little bit longer than the CART. CART stands for classification and regression trees. That topic was studied and thorough, probably introduced to the statistics and machine learning community by a professor named Leo Breiman from Berkeley. Might have been the advisor to Tib Shirani. I'm not positive about that, but somewhere in the back of my head, that name sticks out. Okay, so that's kind of finished. We'll let it run in a second and we'll look at the results. We got a question here. If there's a question, speak out. Yeah? Or is it just an accidental hand raise? Okay. Somebody's got a hand raised. 0. Okay. Anyway, whatever that noise was. So you can see this is why I took the random forest classifier out of the mix here. But it'll finish in a second. And what we'll get here is a comparison between the algorithms. So you can see the results are the 2 numbers it's presenting is how much, what's the mean of the results, which is going to be taken from the cross-val. So what's a cross-validation score? So we in this case, we are going to, the number of folds in our data are going to be, let me get rid of this guy in a second. We're doing 10-fold cross-validation. So you can see it's running the model 10 times. That's why it's taking so long. And I may stop it, but let's give it some more time. It runs it 10 times, so it gets 10 different answers. So the mean is, 99.8%, 99.9, 99.8, 99.9, and then the standard deviation of the 10 folds. And these get graphed here. And you can see you've got, this is your box and whisker plot, right? So the 25, 75 lines are here. The mean is in the middle, I guess. Maybe that's the median. I have to look up my box and Worcester plot again. You got an outlier here. When the last one finishes running, we'll have the 4th one. So based on this, which one is above? Accuracy is very high, given that accuracy focuses on the overall no fraud case. But let's check how well it predicts the fraud case. Choosing one of the model CART results, choosing the model CART from above. So CART, why would we choose CART? Well, it's sort of got the best result, 99.9175. So it's a little bit better than this guy. Here's our last one, 99.5. Let's just pop this over here. So you can see our first validation. You can see that the random forest got you from 99.17 to 9995, right? So it is better by 0.4%. Someone's got a scraping noise if you want to just hit mute on your machine. So you can see this is slightly better, but in the last one, when he had it, CART was the best. So he says, all right, well, how does this best model do on the, and here's what it does. It's okay, do the, create a decision tree classifier and fit it on the train. So notice what we've done here, right? In the loop here, we did 10 folds and we got a mean accuracy on the how does the tenfold work? You 90% of the data is used to fit the model, and then you predict 10%. So these scores are what you got on the 10%, which you did 10 times, right? So you have the mean of the 10 leave one out fields and the standard deviation, right? But then he says, okay, once you decided you're going to go with the decision tree at the CART, right? You then fit the CART on the entire X train set, not on the leave one out set and the entire Y set. And that's what he does here. And then he just goes ahead and he does some fiddly work here. And he says, okay, so let's see what happened here. We were at 99.175. And then when we fit on the two set, we're also at 99.2. So I don't know if it's more or less. But then he also gives us, so what does he give us? We get our accuracy score, which is the first number. We get our confusion matrix, which I believe you studied with Professor McDonald. And we get a classification report. So the confusion matrix is the diagonals are the one we got correct, right? And the off diagonals are the ones we got wrong. So is this right? It seems to me like there should be, no, I'm sorry, this is on the test set, right? So the test set, of course, remember the original data set's 100,000 examples. The test set is 20,000. So you can see 19,000 plus these numbers probably add up to, they may add up to exactly, it looks like they add up to exactly 100,000. And so how did we do? So this many cases were not fraud, and we predicted not fraud. These were not fraud, but we called them frauds. So we were wrong. 7 customers out of 20,000 were inconvenienced. But in this case, there were a total of 54 frauds, and it looks like we picked 45 of the frauds correct, which is actually pretty good. I need to pull up the book for a second. Let me just see if that's the case. Okay, O'Reilly, 1 second here. I'll have my book on my computer. And unsurprisingly, I need to look this up. So let's see what it says. Yeah. Right. So in the book, we have a different picture because we're only using 100,000 instead of, it looks like about 500,000 examples. In the book, it looks like they get all of the fraud cases correct. They get 100% of the fraud cases correct. But the trade-off for the bank is going to be, am I happy getting 45 out of 54 cases? That's like 90% of the fraud has been detected. That's probably considered a good result. And we only cost ourselves 10 improper examples. In the book, The numbers are slightly different, but this becomes a question. This, as you know, my want is I don't, give you the definitive statement of everything that's possible. But the idea is the bank will have to balance between letting a few fraud cases through in order to not have this number go too high. They could push this number down to zero. As we said, if you always predicted fraud, these 9 cases would be called fraud, which would be 54. But the number of these guys would be 200,000 would be moved over here. I guess that's 20,000 would be over here. And that would be undesirable. So this is the kind of discussion that you would have in a credit group, is how accurate do we want to be? And you can go through the rest of this notebook on your convenience. It does a similar type of discussion, similar results, but and it brings another. What I want to do instead is go to the second notebook, and the second notebook, which is and Professor McDonald, one of his main businesses is credit risk analysis. That's his main job. He works for a credit rating agency, KBRA, Kroll, and Kroll Bond Rating Agency, KBRA, which is the fourth largest agency after Moody's, S&P, and Fitch. And their business is about assigning letter grade ratings to offerings of debt, AAA, AA, single A, triple B, et cetera, like that. And that type of analysis, those categories, you actually spend fair bit of time on this in the if you're in the financial risk management program, you would have spent time on this last semester. Credit grades are often tiered into 21 categories, starting from AAA down to AA plus, AA minus, and so on until you get down to D. You get to C, basically you're at risk, and then D, you're in default. That's pretty much the end of the rainbow there. So let's again, the case study. How does it work? We do a problem definition. We do getting started. We load the libraries. We do data preparation. We look at our data, feature engineering, and exploratory analysis. Important topic here is going to be encoding categorical data. We'll see what that means in a moment. And then, how do we evaluate the models, train, test, split, and how do we get a good model? When we get a good model, how do we optimize it? We do a grid search in order to make the model better. So, okay, I'm just checking my time. So much of the same libraries. Again, I've factored out the Keras models. Now, we do get a neural network here. sklearn had neural network models before they got into Google, or so like I was saying about Keras, Google TensorFlow tend to be a little difficult to use, and a researcher there named Francois Chollet. I'll show you who that guy is. Books by Francois. In earlier versions of this course, or of related courses in the program, I used this book. One second. So he wrote his books for Manning Publications. And Manning's another good website for buying books. Deep Learning with Python. This is second edition, 2021. I think the first edition was 2017. So 2017, he created this Keras library to sit on top of Google TensorFlow library. He was working for Google, but he said, we need to make these things better, and for internal use. And ultimately, they released that to the outside world. And Keras was the best way to do machine learning until Facebook came out with its TensorFlow, which they decided was worth developing on their own. Okay, so you can see we get the MLP classifier. So MLP is a term that first was formed in the 1950s and the early 1960s. The perceptron was the artificial intelligence's community's model for a neuron. So a neuron was you have inputs going into your your neuron, which were signals from other neurons, electrochemical signals, and they would pass information to the axon of that neuron. And based on the information, the axon would choose to fire an electrical signal or not fire an electrical signal. And they built machine learning versions of neurons, which basically just said, is it a yes or is it a no? And the multi-layer perceptron was just many perceptrons linked together, causing each other fire, which ultimately became, the concept of a neural network. So in this problem, much larger data set, and we have this one is loan default probability. So different people are asking for a loan, and we need to decide, do we want to award the loan? And they have a data set which says, look, this loan ID number, this loan 3809, et cetera. They asked for 15,000, and we gave them 15,000. Some loans don't always fund in full amounts. You might get, if you're starting a new business, we might agree to lend you $100,000, but we only give you 50,000 the first year, and as long as you show good books at the end of year one, we give you the second amount. Here's the term: 60 months. Interest rates, a wide variety of them. 12%, obviously pretty high. 6%, comparatively better. The grade of the loan person, a C loan paid 12%. In this case, an A loan paid 6.9. What the grades are, we'd have to read in subgrades as well, and then a bunch of other features. And in particular, a lot of that we don't see. We'll need to read more about the data. Okay. So we're going to try to predict the loan status variable. So what is loan status? The loan status is, so this he's telling you, this is what we're going to do. We're going to try to predict loan status, which I don't think came up. Obviously we've got, we got 150 columns. So loan status is buried in there somewhere. It's not at the end, as it turns out. Excuse me. But the statuses are fully paid, charged off, which means we give up trying to collect on them; current, which means they're not paid yet, but they're making their payments; late, up to 120 days; in grace period, which means they've got some kind of deferment; late is 16 to 30 days, so late but not that late; and default 3. So we're going to try to predict the status, and it goes into a variety of fully paid, there's 81%, and charge off is 18%. So he divides them into two categories. He says, make the data set just consist of things that are either fully paid, which means they paid off, or they're charged off. So we're going to ignore the other stuff. Charged off means we gave up. So default means the customer has defaulted under the terms of the loan, but we haven't charged it off yet. We haven't written off the money yet. So after they say, I'm just going to look at those particular two kinds of data, we see that 81% of the data is paid and 20% is charged off. So this is a somewhat unbalanced classification problem. So it goes through more of the same type of thinking we applied in the previous notebook. But if you go through this notebook, you'll see he talks about this full data set has 150 features. We'll eliminate features in the font. So, 150 is a lot of data sets. Maybe they're all relevant, but maybe they're not. But he says instead, you know what? If a feature is missing in 30% of the places, what's missing mean? That's when you have this NaN pop up. I don't, I can't use this feature because it's maybe like only some amount of the, 20% of the rows have this. So I'm not going to use it as a feature because I have to do one of two things. Either I have to say, I'm going to ignore this, or I could say I'm going to make some kind of dummy. I'm going to make some guess as to what this would be if I knew the correct value. So this is just pointing out that your data can be dirty, and you need to think about how do you deal with this dirtiness? Like you can't just say, this is too hard, boss. I'm not going to make a prediction because this data is so messed up. Well, okay, this is the data we have. Either you find a way to derive as much information from it as possible, or you're really, you're not up to the job, right? Not to be so harsh, but that's kind of what it boils down to, right? And then we eliminate features that are unintuitive based on subjective judgment. So you have a story, and the loan ID number is probably not relevant. Maybe it is. And then also eliminate features which have a low correlation with the predicted variable. So if we're trying to predict charged off, and the fact that the person is a man or a woman doesn't tell you much about whether it was charged off or not, well, maybe we'll eliminate that feature in order to make our model more manageable. The more features you have, the longer it could take your model to train, and the less you'll be able to interpret the significance of the variables you collect. And he brings up a list of all of the features he's dropped, leaves us with he dropped 58. So now our new data set has 86,000 elements and 92 features. Okay, that's a lot of features. And then he goes and eliminates some more, gets himself down to 38 features, and still has the same number of rows. And finally, based on correlation, so charged off is, of course, 100% correlated with itself. Notice these correlations are not supremely high, 32% down to 1.5%, right? But what does he decide? He's going to drop. He only drops off less than 3%. So he just says, I'm going to drop off revolving balance. So he only drops off the last four. That's arbitrary. Maybe you pick 4%, you drop another 2. Okay. But he leaves himself with 34 features. And, it's an interesting question for the data scientist, which is, what do I keep and what do I throw away? Data scientists are reluctant to throw away data because I'm trying to use data to inform my decision. So they won't really throw it away. They'll keep it, right? But ultimately, they're trying to build a model that is tractable and they can make sense of. And in particular, if a column contains a bunch of not a numbers and like five elements, well, you're just recognizing somebody started collecting this data, but they really didn't get that far in the process. All right, so 86,000 rows, 34 columns. And he goes ahead, describe, they always type that every book I've seen describe, what just rough, like, what does this data look like? Interest rates, okay, minimum of 6%. So we're in some relatively high interest rate period. Mean is like 13%, max is 26%. So these are possibly consumer credits, right? Where, you do pay 6%. Your credit is only okay. You're buying a car, they might offer you only 13%, right? There was a talk, both Bernie Sanders and I think Donald Trump agreed that, credit card companies should not be charging more than 10%. Well, in theory, you could say, yes, if they can borrow money at 5%, it does seem kind of exorbitant to charge more than 10%. But of course, what credit card companies recognize is that some people are more likely than other people based on their credit scores to not pay back a loan. So when I decide to lend, if I can set the interest rate myself, I can say, look, this is a really bad credit, but I will give them a credit card. I will give them a car loan, at 17% if they want it, because I'm comfortable that with the security of the car plus the person's credit history and their salary, that they will probably pay this loan off. And if they default, of course, I expect a lot more of these people that I'm charging 17% to default than the people who I'm only charging 5%. But I'm making it up by making more money on those that don't default. The challenge with doing things like capping interest rates at 10% is that credit companies will look at somebody with a low credit score and they'll say, well, I can't lend to that person because if I lend to them at 10%, I have a reasonable expectation of losing money, and nobody, you can't force a bank to lose money in a capitalistic, free capitalist society, right? So the people, and this is why every time the idea pops up, whether from the left or the right, that credit card rates should be tapped to 10%, it's never going anywhere because immediately people will start to say, well, yeah, okay, but loans will go way down. And, the problem with not having credit that's fairly priced, of course, it's often one of the kind of pearls of wisdom of Yuval Noah Harari, actually, I think was the one I read this in, was that, what made Western economies really grow. He points back to the 1500s when Italian bankers started with the invention of two things: the limited liability corporation and the invention of interest rates on loans. Which isn't to say that they didn't exist prior. We know the Bible, for example, has anti-usury laws, right? But the limited liability corporation was like, okay, you know what? If I start a company as a limited liability company, then I can take a chance with that company. And if the company goes bankrupt, well, whoever invested in the company will lose all our money that's in the company, but we won't lose our other assets. Now, if I wanted to start a company, and if my company were to go to bankrupt, that would mean that my kids end up in slavery or in the credit house, or I lose my house. Well, I'm not going to take that risk. So risk taking is part of successful capitalism, right? Which is that, I'll take a chance. I'll put 150,000. I'll put $10 million into starting this company, and I might lose this 10 million. But if I lose this 10 million, I won't lose my house. I won't lose my car. I won't lose my 401k. I won't lose my other assets. I'll only lose the assets that are associated with this LLC. The second thing was, differential interest rate pricing. There are ventures which are risky, which people will invest in if they think they can make 20%. They will not invest in them if they think they can only make 8%, because they're understanding that there's a lot of variance around a high risk loan, and they want to have a higher mean to justify that. Okay, that's the off the back. So the one thing they talk about here is that we haven't seen yet in this course, and you probably did see with Professor McDonald, in fact, in his project, you have things like categorical data. Like the employment title, there are 81,000 different titles, 33,000 of which are unique. There are a lot of teachers in this data set. And then, the title, why are people doing things? There's only 20 unique titles, one of which is death consolidation. So you can understand that this category is the purpose of the loan. So you have to look at these things, and what do they do here? Their IDs are all unique, so that's not useful. Too many job titles, too many zip codes. So they drop these. So they drop some of the titles, and he leaves behind. So let's see. By the time we get down to here, I don't think I closed this notebook yet. So I think I can just pop one down below here. And let's just see dataset.coms. So you can see at this point, he's got the loan amount, the funded amount, the term, the interest rate, the installment. Now the grades, we'd seen the grades earlier. The grades were like letters A, B, C, and D. We'll find out that most machine learning models are not comfortable with letters. They are comfortable with numbers. So the grades will be created. A lot of these things like verification status probably is going to be either yes or no, whether or not the income was verified. Let's say home ownership is clearly, own, rent, or something else, right? Own, rent, or mortgage, maybe, and these are categories that can be converted into numbers that machine learning examples can make sense of. And he goes through in this book how to do that. So I'll leave this rest of this notebook for you to go through. And it's kind of clever. And it's worth your effort if you have time this week to go through the rest of this notebook. So next week we'll have one more lecture. We'll have a dinner together, or pizza with the dinner. Professor McDonald will go over his solution to your project. And we'll have one more topic in machine learning, which I'll send you some information on in the week ahead. All right. So that's it for tonight. Everybody thank you for your attention, and I will see you in person in Stanford 7 days from now, minus 3 hours.
All right. Thank you, Professor.
Okay.
Thank you, Professor.
Thank you for me today. Appreciate that.